Hello everyone, I'm Rehan from Team 13. Today our topic is deadlock detection in operating systems. What is a deadlock? Imagine your computer as a busy city with multiple processes working like cars on roads. Sometimes all the cars need to use the same intersection at the same time. When this happens, traffic comes to a standstill. In computing, this situation is called a deadlock. A deadlock occurs when a set of processes are permanently blocked because each process holds a resource and waits for another resource held by a different process in the set. This creates a circular dependency where no process can move forward. Think of it like two trains approaching each other on a single track railway crossing. Each train stops, waiting for the other to move. Neither can proceed and they remain stuck indefinitely. That's exactly what happens in a deadlock scenario in an operating system. Four necessary conditions for deadlock. Deadlocks don't happen randomly. They require four specific conditions to exist at the same time. Let's break them down. Mutual exclusion. At least one resource can't be shared. Only one process can be used at a time. Hold and wait. A process holds at least one resource and waits for more that are held by others. No preemption. Resources cannot be taken away forcibly. The process must release them voluntarily. Circular wait. A closed chain exists where each process is waiting for a resource held by the next process, forming a circle. If any one of these conditions is missing, a deadlock cannot occur. Resource allocation graphs visualizing deadlocks. To detect and understand deadlocks, we can use resource allocation graphs. These are directed graphs showing which process are using or requesting which resources. Vertices, circles represent processes. Rectangles represent resource types. Request edges, arrows from a process to a resource indicate the process is requesting that resource. Assignment edges. Arrows from a resource to a process show that the resource is already allocated. Deadlock detection. If the graph contains a cycle and the resource type has only one instance, the system is definitely in deadlock. If there are multiple instances, a cycle indicates potential deadlock and requires further analysis. By visualizing the resource dependencies, this way we can detect and prevent deadlocks before they freeze the system.
Hello, this is Alan. From here onwards, I will continue. Let's begin with an overview of deadlock detection algorithms. Different detection strategies are used depending on the system design and the number of resource instances available. When dealing with single instance resources, we can use a simple cycle detection algorithm in the resource algorithm graph. If there is a cycle, it means a deadlock exists. Now let's take a closer look at how the wait for graph algorithm works in practice. We start by creating a directory graph where each node represents a process currently active in the system. Next, we draw an edge from process Pi to Pj, where Pi is waiting for the resource and the Pj currently holds. Once the graph is built, we apply a cycle detection algorithm such as depth first search. If a cycle is found, it directly indicates a deadlock. The main advantage of this method is that it simplifies the graph by removing resource nodes, which makes detection faster and more efficient, especially in systems with many processes. Once a deadlock is detected, the system must take steps to recover. There are three main recovery strategies. First, process termination. This can be total, where all deadlocked processes are stopped at once, or selective, where processes are aborted one at a time until the deadlock is resolved. The choice can depend on the factors like process priority, how much work has been completed, and resources held. Second, resource preemption. Here we temporarily take resources away from the certain processes to free them up for others. We can carefully select the victim process to minimize the overall cost and make sure no single process is unfairly targeted repeatedly. This helps prevent starvation. So each of the methods has its trade-offs between the performance, fairness, and the data consistency. So the choice depends on the system's requirements.
This is Vamsi. I will be explaining from here. Deadlock detection is critical for system stability. It prevents freezes that could halt operations entirely. Let's look at the real world deadlock scenario. In a banking system, transaction T1 locks account A and waits for account B, while transaction T2 locks account B and waits for account A. Both wait on each other indefinitely. A perfect example of a circular wait condition. The database's deadlock detection algorithm spots this cycle, aborts when transaction releases its logs, and retains it automatically. This ensures smooth recovery without system crash. Deadlock detection is critical for system stability. It prevents freezes that could halt operations entirely. It also optimizes performance by balancing detections overhead with system throughput. In mission critical environments like healthcare or aviation, timely detection isn't optional. It's essential for safety and reliability. As a system grows more complex, preventing deadlocks become a major design challenge. Future innovations may include AI that predicts deadlocks before they occur, hardware assisted detection, and even blockchain style distributed coordination, just like managing traffic, detecting and resolving deadlocks, keeping computing systems running smoothly.
Let me explain deadlock with a real life traffic example. Imagine a four-way intersection with no traffic lights. Cars from all four directions enter at the same time and stop in the middle. Each driver waits for another car to move first. But since everyone is waiting, no one can go forward. This situation is called a deadlock because all vehicles are stuck in a circular wait. In computing terms, each car represents a process, and the road space is the resource being used. A deadlock can be detected if traffic cameras or sensors notice that all cars are waiting and none are moving. To solve it, one car needs to reverse or a traffic controller can intervene. Adding proper signals later helps prevent such deadlocks from happening again.